everybody. We're over here at my good friend Carl's shop, and he asked me to do some filming. We're going to show you some cutoff technique here, and we have some video also from a friend of his, and we'll get into that a little bit further. But we're at the 10EE here with Carl, and he's going to have a little discussion about what we got here.
Yeah, this project started years ago. This particular Monarch came with a air closer, air collet closer, and a turret. And I got rid of the turret. The air collet closer had long since gone, and I needed to make a collet closer. So here it is. And interestingly enough, this is a piece of 1-inch black iron pipe, Schedule 40. It's exactly the right size for a 5C collet drawbar. Unfortunately, it's not quite as straight as drawn over mandrel tubing, but hey, works for me. And the immediate problem was to secure the hand wheel to the tube itself. And I looked at this and I thought, well, I can do it on the mill by moving, setting this off the table and moving the ram and the head over, way over, and you know, doing something. And I thought, well, I can also do it on the lathe. So what we're going to do now is we're going to move in and we're going to look at the drilling attachment. So in order to drill and tap those 6 holes on the bolt circle, I built a drilling attachment for the lathe. This is fairly simple. It's just a phase 2 or other import boring bar holder with a 1-inch bore. And I had a pair of oil light bushings with a flange, 1-inch OD and 3/4 inch ID. So I just simply jammed those in each end. And then underneath this collar and underneath the sheave, there are needle thrust bearings. So the rest is pretty straightforward. A piece of 3/4 ground stock was drilled to match the taper on the drill chuck, and a standard shaft collar closed up this end, and there it is for the drilling attachment. In order to convert this to a sawing attachment, I realized all I had to do was utilize the 1/4-20 hole that was already into the shaft and make a couple of little pieces to I had to adapt to the 3/4 inch shaft to a 1-inch bore slitting saw, and then a clamping collar. And so there it is, and we're going to see this in action as a sawing.
So you'll hear a humming background right now. Carl, explain that you have the 10EE set up on 2 different methods for power, right?
That is true. It retains the original Thyratron drive, which I don't use, and it also has a GE Fuji DC 300 electronic drive, which I use, and that's buried in a cabinet down there, which you really can't see. But what you hear in the humming is the phase converter for the GE drive. Now, to finish the attachment, this is a Baldor 1/4 horse 3-phase motor, and a 115 volt to 240 volt 3-phase VFD, and it's currently set. I'm driving the saw at 1000 RPM, which is probably a little high. It's what Jim drove his attachment on, and we'll get back to Jim here in a little while. But what we're going to do, we're going to saw a little disc off of this piece of aluminum. The purpose of all this, getting back to Jim, and we'll try to put that video ahead of this so you see what he was doing. He wants to cut a 32nd wide by roughly 200 thousandths deep grooves to form the fins on a cylinder for an engine that he's building. And he's doing it with a CNC mill, and he got to wondering, well, can it be done on a lathe, and what would happen? So I agreed to set all this up, and we're going to run this thing and show you what it does. Got to turn the DC drive on. Now, one of the problems driving this slitting saw at 1,000 RPM brings up the question of surface feet per minute, your cutting speed. And because the tooth is in contact with the work for only a very short period of time, but the rest of it's in the air, 1,000 RPM doesn't seem to be a problem. I did keep the spindle speed down just to avoid any problems, and I'm not using a lot of feed. If I can get Chuck to pass me the coolant.
And you're running the lathe in reverse.
Running the lathe in reverse that way, and the teeth are pointed so that the chips go down. When I first started this, the chips went up, and it makes a mess. So now the chips go down, and I'm not climb cutting, I am conventional cutting. So we're going to go up, start this, touch off. I want to part this off completely so that we can measure the thickness of the full washer.
So the shaft was already faced on its end.
Yeah.
And the goal is what? What's the goal of the thickness?
See how close we get. Oh. I can't set any tolerance because this is the first time I've done it. I don't really have a good idea of what it will hold. You know, in part, how well this works is how sharp the saw is.
Yeah.
It's a used saw, and so, you know, there's a lot of variables in this.
Got it. Am I in your way?
No. Oh, look at this. Well, we're not going to do a lot of thickness measuring. I was hoping to get thickness all across the width. It turns out it went,
The heat.
yeah, probably from the heat. It warped.
Yeah.
But it was not apparent that it was warping as it was cutting, but it must have. So I'm not willing to draw any conclusions on this yet. I am suggesting that this is just another arrow in the machinist's quiver. It's something that might work, may help you get out of a problem if you need to cut thin pieces that are fairly deep.
But actually, if you were emulating what Jim was doing, it would work.
It'd probably work, yeah. Let's see, how far in did we go? Half inch.
Half inch.
And a conventional parting tool, 32nd wide, going in a half inch, would certainly have problems with the chip.
Chip, yeah.
Well,
And what was the depth Jim was cutting?
he was cutting aluminum,
But how deep? He was only going.
150 to 200, something like that.
Oh, was that okay? Was that deep?
Yeah, it wasn't any. It was about half as deep as we went here, maybe and less. What we can do, just to demonstrate things, we can take this off. We will clean the end.
Oh yeah, I like that. I'm going to stop the camera and we'll flip to the other side.
Okay. Okay, I'm going to demonstrate how square this is, or find out, by facing the end of the bar off. But before I do that, I want to know if there's a warp or out of square. Is it on the outside or on the inside? So I just put the indicator on here. And I go 0 to plus 2.5 and back to 0. So this is the low and this is high, I think, and we'll see if facing this confirms that. Yes.
Yeah, right.
Yeah. So the slitting saw was moving a little bit, and that implies that the teeth were not fully sharp or other operating problems. But on the other hand, what I'm going to do is I'm going to zero the travadial, and I'm going to see if we can get some rough idea of just what the difference is. About 2 thousandths, maybe 2.5. So that's not really terribly bad.
No.
Okay, there you have the demonstration. Like I said, I don't know how useful this is. Again, it's just a suggestion for other people to take up, experiment with. Maybe it'll solve a problem for you sometime in the future. Now we're going to go back and pick up Jim's videos and pictures and integrate them into this. We'll see how this turns out. This is another adventure for Chuck and I.
We like adventures.
Yeah. This is where it all starts. This is the engine made by Jim, who I mentioned in the video over on the lathe. It is a 5-cylinder radial. It uses Cox 049 cylinders and pistons and glow plug fuel. I don't know where he got the design, and I think he modified it substantially for his own purposes. But we're going to see right soonly in the video clip how well it runs. About 18 years ago, Jim made a pair of Upshur engines, and I forget whether these were published in, plans were published in Strictly IC or Model Engine Builder, but he built them. They were okay first engines, and this year, after he finished the 5-cylinder radial, he wanted to upgrade them. One of the first things was to install new pistons and cylinders. So we see in this photo and the previous one, the cylinders. There's a cylinder sitting off by itself. And in the next videos, we're going to see how he made those cylinders. we're back to Jim's five-cylinder radial engine, and what started him off on the small fins was looking at these cock cylinders and wondering how they made them on a production basis. And he decided that the best way in his shop was to do them on his CNC mill. It's a Bridgeport that's been converted, and he sure enjoys working on that one. Now, if we were to move from his shop to my shop, I would have to do this, if I were done on the mill, with a rotary table and cranking it. Well, it's a powerful lot of cranking, and it's always hard to get an even feed. So his idea was, let's put this project on the lathe. And I already had the spindle built for the drilling attachment, and so I went ahead and did the lathe work. So once again, I hope this is useful, something to play with. Might get you out of a bind at some time in the future. And in any case, Chuck and I had fun making the video, and I certainly hope you had fun watching it. Thanks a lot.